Hi, can you all hear me? Hello, I'm guessing it's clear. My name's Narusha Isaacs-Klein. I'm a PhD student at the University of the Western Cape. Um, I'll be giving you a little bit of an not too technical talk with regards to astronomy and SKA. So the basics of astronomy comes from what everyone knows as the periodic table. These elements are found in space, and these are just a few ways in which these elements are created, or how they are created in space. Um, so I put this up just to show you that even the basic physics that we learned in high school plays a big role within astronomy research. Um, so there's various branches within astronomy. Some people focus on large scale structures to very small scale structures. Um, Basically, the largest scale would be cosmic web. Then there's galaxy clusters, galaxies, galactic structures, planetary systems, asteroids, asteroid belt, the comets, interstellar medium, nebula, star clusters and individual stars, and then there's meteoroids, meteorites, and that's from largest to smallest. Something that I particularly focus on is galaxies. And this is just an image of the various types of galaxies that you get. Within these categories, there are subcategories as well. Um, so uh, there's lots of astronomers that focus on stars, and galaxies are made up of lots of stars, and this is just the life cycle of what a star would go through and how they form and in their different forms and in their life cycle. So I just put up a picture of Hubble and the James Webb image. The reason I did this is because when I was in my honors year, I worked on Hubble data, and now looking back at what I've done in my research in honors, I think if James Webb was available at that time, I would have had an easier job. So it's very nice to be involved in astronomy at this point because it's evolving so rapidly, and with technology that's continuously evolving, we get to witness um, all the different aspects. So if you just look at the comparison, these are exactly the same images or the patch of sky. And you can see that in Hubble, you don't notice all these little galaxies, and every little dot here is a galaxy. So it's just to show how clear James Webb is. And this is the reason James Webb is way more clear than Hubble. So Hubble's primary beam, or if you look at a camera, um, was this tiny. And now with James Webb, it's much bigger. So it has a collecting area that's way bigger. Hence the image is way clearer, and they can detect finer details. I put a little picture of the black hole because everyone is always interested in the black hole, even though I don't study it myself. It's something that's been a hot topic for a while now. So this was simulations throughout the years, and then we finally got this image, which is just made up of multiple images put together. The Event Horizon Telescope is um, what made this massive discovery, and um, now we get into why astronomy is so important in South Africa, and why we were privileged enough to be part of the SKA. SKA has these two sites, as you can see. SKA telescope telescopes are a game changer for radio astronomy. So there is the two world-leading complementary radio telescopes on these two continents, which will revolutionize our understanding of the universe and even laws of fundamental physics. The telescopes will cover two different frequency ranges. So here in South Africa, we'll have SKA mid, which is the mid frequency range. We will have 197 traditional dish antennas, and that will be in the Karoo region. And then in Australia, they'll have SKA low, which will be an array of 131, I think 131,000 small tree-like antennas. And that's being built in Australia. So you can see that there's a very different shape. So theirs is the antennas and ours is dishes. The arrays will both be spread across large distances, and that's why the Karoo is very important for where it's located, is because there's no light pollution and the open skies. And that's why one reason why we got the opportunity to build this telescope in South Africa. So using cutting edge technology, including some of the fastest supercomputers in the world, will make it possible to study the universe at exquisite details, revealing the inner works of galaxies and helping us to understand the extreme environments around black holes, tracking the journey of gravitational waves, and enabling us to have ambitious science investigations. So something that's already existent in South Africa is called Meerkat, which is the 64 dishes. And that's active and it covers 9,000 square meters. This is just an image of the South African Astronomical Observatory, which is based here in Cape Town. And this was established in 1820. It's extremely old. There is still people that use this telescope. There's night sky viewings. There's open nights for the public to go. As you can see, the surroundings is now polluted with light, and hence there's no new telescopes there or anything like that. But the facility is still used for astronomers, and there's an outreach office there and a astronomy for development office there, and there's lots of astronomers that have offices there. So this is just an image of how the Karoo looks. This is one of the telescopes, and as you can see, not one of the telescopes, one of the arrays, all the arrays together make this telescope. So as you can see, there's a human standing right next to one. And if you can imagine, 197 of these are going to be spread across this area, and making it possible for us to see the faintest details, which is going to be really, really interesting for astronomy research. So this is just a large scale of where the SKA falls within telescopes currently. So SKA low, like I told you, would be in Australia. And if you look at the amount of square kilometers it would cover is going to be way more than what currently exists. And the amount of antennas is going to be way more than the amount of the antennas that currently exists anywhere else. The South African part, which is SKA mid, is going to have 197 dishes, which is more than anything currently. Meerkat is just a precursor for SKA. And currently, the best competition for SKA mid would be the JVLA. And the telescope's capacity is going to be so faint. So the sensitivity is going to be so faint. And this is because the collecting area is going to be so much bigger. So like I said, it's going to spread across a large portion of the Karoo. And if you think about the JVLA, it's not even like compatible really, because of the amount of details we'll be able to see, and the resolution will be really, really great. Then we have other telescopes in the world, which is mid-frequency, and then there's the high frequency range, which we'll use to study multi-wavelengths, so use images and compare them with the same patch of sky. Just more on SKA. If you look at this image in the bottom, that is a comparison of what SKA mid on the left would be like, and then the same frequency range for the JVLA, which is in the United States, and it's 4 times better than the JVLA. The problems we foresee is the fact that with the SK, we'll have 8.8 terabytes of data per second. So we'll need to store this. But there'll be pipelines and we'll reduce the amount of data that we'll store. So that's currently what a lot of astronomers are working on also. Some fun facts about the SKA. So the SKA telescope is going to be sensitive enough to be able to detect an airport radar that's on a planet 10 light years away, which is really, really cool. And you'll be able to see those details. So every year for the SKA, we'll be able to fill 1.5 million 500 gigabyte laptops. So storing of this data is quite tough, but that also gives people lots of opportunities to invent things and infrastructure that can hold this. Gives engineers lots of opportunities to develop the infrastructure. Another thing is the computing power of SK. So the supercomputers that is being developed is 25 times more powerful than what the best supercomputer is. So that's what the engineers are working on. And then we have the data flowing from antennas on site, which will be about 65,000 times faster than the projected global average band speed. So basically your internet access. And it was done in 2023. So it's still kind of the same. And this was, I think, 110 megabits per second at that time. So a picture is worth 1,000 words, and I'm going to give you just a bit about astronomy that I do and why Meerkat and SK has been impactful on my work. So this is just an image of Meerkat, and so the survey I'm working on is called Laduma, which is looking at the distant universe with Meerkat Array. So in South Africa, as all of you know, the vuvuzela is something that's very popular, especially after the 2010 World Cup. And then we named this survey after that. So it took a while to get the name going. Astronomers are quite creative with naming things. Like we have a survey and things like named Samba and things like that. So it's really cool. So the Laduma survey has been confirmed by International Review Panel in July 2017, I think, as one of the top ranked large survey projects to be performed with Meerkat. And that I said is the precursor for the Square Kilometre Array. So working with us has been absolutely amazing. And this data, while we're still waiting for the rest of the 64 antennas to be added, we've gotten data thus far to work with. As you can see on the left, this is just a galaxy. And this is something that I've been working on in my PhD. So I work on multiple galaxies, and while this galaxy is quite nice, you can see like some of the spiral arms, some of the formation. This on the right-hand side is something we call the positional velocity diagram. And from this, you can infer a rotation curve. While that galaxy was very nice, we do have these faint galaxies, which we kind of need to also infer rotation curves from. But as you can see, this does not have the same shape as the previous one. So having said that, the fact that the shape is not the regular shape of a rotation curve, we have to use simulations and modeling, and that's something that I've been working on. So this is just the two galaxies. And as you can see, the rotation curves varies quite a bit with different galaxies. So what's going on in the data? The data we get currently is not the top of the notch data that we're going to get once SK is up and running, but we have to do something with it while we have it. So trying to work with what we have and see what we can get. So I've developed a modeling method using one of the packages that's already available in Python, which is what we use for coding. So this is the data that I have, and this is the galaxy. This is my model of the galaxy. And then we'll be using this data along with the data that I've just mentioned from the Laduma telescope. And then we'll be inferring a rotation curve, but I'll also be getting a angular momentum estimation for these galaxies. So this is the reason for this modeling is so that we can model the smaller galaxies, and the smaller the galaxy, the more difficult it is to work with. But the biggest part is the fact that now that I have this code going, or this modeling technique going, I can model the small galaxies the way I've modeled this big galaxy. So this is back to the Laduma data. And we use this data in conjunction with this image in conjunction with the Laduma data to get out angular momentum estimation, and that we'll use also to get our rotation curve. While I'm still busy with all of that, because my PhD is still ongoing, hopefully I'll finish soon. Something that I want to tell you all about is something that's super exciting within South Africa. It's called the IAU General Assembly, which is basically the World Cup of astronomy. It's like the biggest meeting within astronomy, and this is going to be the first time it's going to be hosted on the African continent. So it's going to be on the African continent for the very first time, which is super exciting. And it's going to be in Cape Town. There's going to be a lot of activity around this time. There'll be a lot of outreach activities where we'll go into communities and spread awareness with regards to astronomy. Personally, I want to go to the more rural communities, as the closer you get to Cape Town, more people know about astronomy. But the further you go out, they haven't really heard about astronomy, what it is, and the opportunities that there is within astronomy. Besides just astronomy, there's lots of funding within astronomy for engineers as well. So it's really important to know that while the science is funded, there is also engineering opportunities that is funded. And if you want to know more about the General Assembly, you can contact me. You can contact me with regards to anything. If you want more information with regards to any of the topics I mentioned or astronomy in general, because my colleagues do different parts of astronomy where I just work with galaxies at this moment in time. That's my field of expertise. I do have colleagues that work with cosmology and other parts within astronomy. So if you have any questions on that I can't specifically answer, I can get them to contact you, or you can email me and I can get the answer for you. But I'll try to answer any questions as best as I can. That being said, I'd like to say thank you to the organizers for allowing me to speak and giving me this opportunity to share a bit of astronomy and the opportunities that there is within astronomy. That's my email address. And then my colleagues and I have started something called Future Leaders in Color, where we give talks and we help underprivileged community kids to do better in school, in academics, and hopefully they get into university to better their circumstances. Our main aim is always to give back and create awareness within the STEM fields. It's not necessarily that everyone will go into STEM, but just giving everyone the opportunity to do something after school is our aim. If you want to know more about our little organization, you can contact me. You could, if you want to get involved, if you want us to come out to your school, you can contact me and we can make a plan. Thanks again. I can't hear anything.
Can you hear me now? No.
Yes, I can.
Okay, right. Anybody got questions, or can I fire off with one? No. I don't have one. It's fine. We can just talk over the laptop mic. All right. So, couple of questions. Just on the SKA, can you just remind us of the timeline and where it is and when it's going to start? In 100%.
So with regards to the current SKA, within South Africa, we have 64 antennas already built. The others are still being built. Australia actually released a statement, I think, early March now, that the first antenna has been built. Or I don't think it has been built, but like it is in construction, like most of it's been built. So it's still very much in construction. The predicted date keeps changing. So I don't want to say, oh, 2024, 2030, 2036, and then it's not going to be that way. But as things stand currently, we have our 64 antennas, and they have started their our 64 dishes, and they have started their first antenna. I'm just trying to find an image that I can share with you to show you what they have built so far. Just give me a moment. Okay, let me just share my screen again.
There we go.
There. So this is what the antenna currently looks like. And this was released on the 7th of March. So this is how it looks currently, and that's just one. So looking at how far it's come, I don't want to give any predictions as to how long it's going to take to come on board. Hopefully, while I'm still within my early astronomy career.
Okay, thanks for that. And Elaine, did you have a question?
Relating to the work currently she's doing, the model that she's working on, does everyone use the same model, or is there one model that everyone uses, or is this a personal model? And then the other question is, where does she currently get her data from for that, her modeling?
I don't know if you heard that, Narusha. Must I repeat it?
I did not hear,
Okay,
unfortunately.
so Elaine was just asking on your modeling that you work on, does everybody use the same model, or have you got your own personal model? And where do you get the data from for the model? So this is the gist of Elaine's question. Do you want to come here?
Okay, so for that part, I'm using a soft, well, a package within Python, but not everybody uses the same modeling technique. No one used this within the Ladoma collaboration. There is multiple ways in which you can model this galaxies. I only used it because I was interested in a specific outcome, but I have also tried other methods. I am trying other methods as well. So the one with the best outcome is going to be the one I'm going to use. Currently, this is the best that I've managed to get, but it does not mean that everyone uses the same.
Thanks.
And a lot of people use simulated data as well.
Another thing which is quite fascinating to me is I didn't know there was such a variation in the rotation speed of different galaxies. I thought they were all that relatively flat to the outside, where the outside is going much faster than it's supposed to, if there was only the visible mass that was driving it. So what is the theory with the others that are going closer to a normal speed on the outside, a much slower speed? I presume the theory must be that there's less dark matter there, or what is the sort of, is there a current theory?
So there's different theories with regards to that. And also something that plays a role in how the galaxy is rotating is whether it's merged with another galaxy, so how much matter it has, how much H1 matter, how much and H1 just meaning neutral hydrogen. That is what the Meerkat telescope is detecting. So it really depends on the content within the galaxy, how fast that is rotating, and also the shape in which the galaxy is. So I don't know if you remember earlier in the talk I showed that galaxies have different shapes, where there's spiral galaxies, elliptical galaxies, irregular galaxies, they all rotate differently. And sometimes there's a galaxy that will be in the process of merging with another galaxy, and that will also affect the rotation curve of that galaxy.
And then what is a globular cluster? Is that a galaxy, or is it a sort of failed galaxy? And does it rotate or not? So did you hear my question?
Sorry?
So did you hear my question, Narusha? I just asked,
No.
what is a globular cluster? Is that a galaxy, or is it just something else?
So you're saying, what is a globular cluster?
Yeah, so we have several globular clusters, which I think are relatively close to the Milky Way, for instance. Are they failed galaxies?
So the globular cluster is not a galaxy. It's more like a densely packed spherical collection of stars bound together, but it's not like a general galaxy, if that makes sense. It's
Okay.
just like a lot of stars that's bound together.
Okay, thanks.
It's
Any more questions?
kind of.
Yeah.
Just in terms of the blue that showed Australia to have the biggest sort of area of the SKA and Africa the second most. In South America, there's just one little blob of blue on the east side. Is in South America not part of it at all?
The question is the small blue blob showing the in South America. Is South America not part of the SKA? Is that just a different radio telescope on a two discs or in South America?
South America is not part of the SKA, no.
Okay. Is there is an array in the US, isn't there?
Yes, but it doesn't fall within the SKA arrays. They do have partnerships with us. So some of them is just funding partnerships. Some of them have observatories that will use data from the SKA, but the SKA telescopes will just be, or the array and the antenna will just be in South Africa and Western Australia at this point for this part.
Another question, yeah?
She mentioned the materials that were other foreign to Earth or space material. Does she know anything about the qualities of these materials? How many are they radioactive and dense?
Sorry, somebody just asking about the materials you mentioned that are foreign to Earth. I think I missed that. I'm not quite sure. He's just asking, what are the sort of properties of these materials?
So there is stuff, there is properties of these elements that are in like dying low mass stars or merging neutron stars. So that's a lot of the elements that's on the bottom of the periodic table. Those are on the merging of neutron stars. There's lots of that, and there's a lot of the dying low mass stars, if that answers the question. The higher on the periodic table would be the exploding massive stars, exploding white dwarfs. There's also the two elements that came from the Big Bang fusion, which is the hydrogen and helium, and some lithium.
Okay, so there are materials in outer space due to the neutron mergers and so on, which are common there, but not common on Earth.
Yeah.
Very dense.
Yeah. Some would be heavy elements, and other different reactions would be like some of the lighter elements.
Yeah.
One more question. Yeah.
Does everyone have access to everyone, or is restricted? You know, like Georgia can anything she likes, or
Okay, so the question is, with all the various telescopes out there and all the data being produced, do you have access to all of it, or how does the access work? Is it do certain scientists sort of book a certain slot, or how does it happen?
Yeah, so unfortunately, we don't all have access. That's why it's always nice to have partnerships or collaborations. There is this, because it's in South Africa, we'll have, or that this is the notion, because you don't know what's going to happen in the future. We can't predict, but there is the fact that it's here and there's funding coming from South Africa also, that we will have access to the SKA data. But from all the other telescopes in the world, you have to apply for data. So you apply for time on this telescope, on whatever telescope you want. And if your proposal gets accepted, you'll get to use that telescope to view a specific part of the sky. Your proposal needs to be very specific as to what your scientific goals are, or what you want to use the data for. Something that is very tough within astronomy is applying for data and not getting it, which has happened to me personally. So yes, so that, I guess, I understand why it's this way, because if everyone had access to all the data, then it would be very difficult to control who's working on what. Because, for instance, if you look at the survey I'm working on, which is the Laduma survey, we have to apply to use the data, but we also have to say exactly what we want to do with the data, so that there's no overlapping projects. So that someone might be working on something for 2 years and someone else comes in and works on the same thing, but manages to do it quicker and publishes it. And then it's like, this person's been doing it for a while. So there is that reason as to why it's not public, but there is publicly available data. So I think that, because this is what's going to happen with Laduma data, after a certain amount of time, the data becomes public and everyone is allowed to do any science with it that has not already been done. And that gives any astronomer all around the world access to this data. So yeah, it is there's a time period where it is on an application basis, where data is already available. Then there is where you can apply to specific telescopes to have time, so that that data is specifically for your project, if that makes sense.
Okay, thanks. I know some of the historic data from Hubble and even JWST is available for public. I've manipulated some of the JWST, the early images myself, and done my own processing on them and so on. So that can be done, but I think it's at least 8 months or a year before it becomes publicly available.
Yeah.
Okay.
There's always this time frame and time period before it becomes publicly available. That's why it's nice to, if you want specific data, if you work in collaboration with someone that already has access, but it's give and take. What are you going to give me to have access to my data? Because then you work in collaboration with someone else. You help them with their project, they help you with your project, and kind of works out nicely, especially if it's in different wavelengths.
All right, thanks. Any more questions? One more, okay. You can come up and talk here without a remark.
Narusha,
Yes.
why is the layout of the ground stations for the kilometre square array telescopes in Africa in a logarithmic spiral, like a Fibonacci curve?
I'm going to be honest and tell you, I have no idea.
Engineering.
I have no idea.
I think that's probably for efficient distribution of.
I'm assuming, I can assume, but just don't quote me on this. But previously, when I did lots of research with regards to telescopes and things, something that they try to optimize is getting the most area, like receiving area from outer space. So the bigger the area, the more light you can capture. And then also having this being received and not contaminated. So there's something where your own data can contaminate your own data because it will reflect on each other. So maybe something like that, but I just assuming.
It's an engineering solution to minimize noise and optimize the
Yeah.
Thank you.
So that's why there's lots of opportunities currently for engineers to optimize everything and also make it more cost effective, because building telescopes is super expensive. So the more they can save us some money, the more we can build.
Okay, thanks very much. I'm sure that in your outreach capacity, we will probably be contacting you in the future. We have our outreach director of the Astronomy Society of South Africa is actually with us here tonight, and he is with us in the Hermanus. And we do a lot of outreach, so that's possibly something we will be contacting you in the future. So
Yeah, that would be really great.
we'll take you up on your invitation there.
Yes, definitely. I'll
All right.
come out and bring some of my activities and get everybody interested in STEM, whether it be in the science side or the technology or infrastructure or something, just sparking that interest is all we look for.
Great. So I just want to say then, thank you very much for a fascinating talk, and you've enjoyed it. Can we give her, can you hear us clapping? I put my video on and you can see the people quickly. They are there, they're real. Okay. All right. Thank you very much.
Thank you so much, and thanks for having me. And I hope to see you all in person soon.
Okay, great. Thank you. And goodbye. I'll send you a link to the recording.
Okay. Thank you so much.
Thank you. Okay, bye.